But we'll move on to our next presenter. We have Ahsan Iqhal, and he's going to talk to us about the frost resistance of low carbon concrete. And you can ask questions still on the chat, and we'll come back to them after the presentation. And we have also time at the end of this webinar. So we have 45 minutes reserved at the end of this webinar. So all of your questions will be answered, don't worry. But I'll give the stage to Ahsan. Go ahead.
My name is Ahsan Iqhal, and I'm currently working as a project member in LOIKKA. I worked on sub-project 2, which is frost resistance of low carbon concrete. And yes, so we divided it into 2 phases. The first phase was basically when I started like back in February 2022, and it was my master's thesis project, and I did this phase of LOIKKA as on effect of slag content on frost resistance and compressive strength. So moving on with the results that I received. So compressive strength, we used 9 different binders, and overall in this phase we used like 9 different binders with different slag contents from in the incremental way from 0 to almost 80%. And if we look at the graph closely, we can see that starting with the blue ones that are like 7 days, it shows that when the slag content is increasing, the initial compressive strength is decreasing. So it means that the slag is like lowering or delaying the hydration process. Then if we look at like the 91 days, so it shows the incremental increase, and if we see it, so basically SEM3B achieved the highest compressive strength, and it's like even more than SEM1. And if we look at the 28 days, so it's like you can see like the irregularities. So slag didn't have like a direct effect on the compressive strength. Moving forward with the frost resistance, so we measured it with 2 parameters. Firstly, I will explain scaling, and it's like the surface abrasion. And we did like also for 9 different binders, and 2 types of samples were used. One was like non-carbonated, and the other one were carbonated. So if we look at the first above graph, so we can see that the non-carbonated had quite a lower scaling than carbonated ones, and it also basically satisfies the standards, except the OIVAs with 80% of slag. And the strictest scaling standard, like the surface abrasion or the surface scaling, was 0.65 kilograms per square meter, and it also depends on the exposure classes and the service life of the structure. So if we compare it with the carbonated samples, so we can see that the scaling has been quite high in case of 3% of saltwater solution, and it was because the carbonation concentration was quite higher and it was quite harsh. If we look at the deionized water part, so if we look at the y-axis, the values are quite small. It's in decimals. So we can derive from the graph that the carbonated and non-carbonated samples worked or resisted the frost resistance quite well. Another parameter that we discussed or that I worked on was internal damage using UPV, and it was also for salt water and deionized water. So if you can see the dashed line, it was the strictest requirement, it's 85%, and you can see that all of the carbonated and non-carbonated samples passed that standard, except for the non-carbonated with 80% of slag. And if we turn towards the deionized water, so with quite margin it passed this frost resistance standard. And here I would like to mention that for the case of deionized water, this UPV or internal damage was a better parameter to show the results than scaling. Moving forward with carbonation depth and its correlation with slag. So if we, on the x-axis, we have from 0 to 80% of our slag increase. And if we look at it, so if the slag content is increasing, so as the carbonation depth. And the carbonation depth here is quite large. That is like in reality 5 times or more than the actual case. And the reason was the carbonation, carbon dioxide concentration in the carbonation chamber when we kept the samples there for 62 or like approximately 2 months, and the concentration was 3 plus minus 0.5%. And we did this because of a bit of time constraint. So I'll also, like you can see the 2 different pictures of the carbonation. The uncolored or like the non-pink borders that the samples have, here we can like measure how much the carbonation depth was. So like with 0%, it is clearly showing like a lesser CO2 depth than with 80% of slag. Another factor that we discussed or that we examined during our project was P factor, that is usually used, that is mainly used by the Finnish Transportation Agency for studying the service life of the structure. And here we can see that if with the decreasing slag, or if the slag is lower, we have more P factor, which shows that the concrete material is more resistant to freeze and thaw, and it shows like it will have a higher service life. Okay, so after the completion of phase 1, now we are in the state of in between the stage of phase 2, and basically the answers we are looking for are how the aging factor or the carbonation will affect the freezing and thawing. I would say it is still quite early, but still we have some results that basically confirms the results we got previously during phase 1, and basically we are studying the effects of testing age and carbonation on frost resistance. So if I give like a brief idea, what we are trying to get from this program is to check the effect of curing, time curing, and like how much time it will be, what will be the effect of it, and also the aging factor. So here we are using 3 different binders with different slag contents. The first is like, and also all are from Pika, and SEM1, SEM3A, which have like 40% of slag and 60% of Pika. I would like to mention here is like all the cements are SEM1, but the recipe we used makes it like of SEM3A and SEM3B. In SEM3B we have 70% of slag replacement with cement clinker. And the testing age we will be doing are like normal procedure that I showed or explained in the during the phase 1, without like when the concrete is of 28 days, and then the starting test date is 31 days. Then moving on with 3 months testing, when the concrete will age 3 months, and then 6 months, and then after 1 year. And also like the aging, we will be discussing the aging conditions as well. So some of the samples that we will test at 3, 6, and 3 months, 6 months, and 1 year. So they will be placed in water, also in air, or just like relative humidity room at 65%, and we will get natural carbonation of that that is present in the room. And also like the other samples that will be plastic, that will be protected or wrapped into the plastic, so we don't get we don't get to expose it directly to the CO2. So currently we finalized the first normal testing that was initiated after 28 days, and basically these are the same results that I showed during phase 1, and it basically confirms the behavior for all the 3 cements. So we can see that when with no slag, the scaling in kilograms per meter square, it's quite low, and as we increase the the slag content, the scaling of the surface that is exposed to freezing and thawing increase as well. Then moving towards the carbonation depth after 3 months when they were aged and placed in the relative humidity room. So here it is basically a natural carbonation phenomena, so we are not concentrating anything, but like the naturally present CO2 concentration is usually 0.04% in the atmosphere. So we are basically altering that. So here we can see like the whole surface that is tested, it turned into pink. I would say it doesn't have any carbonation depth for SEM1, and here we are basically comparing the plastic protected and carbonated samples. If we move forward to SEM3A, so it had like couple of decimal points of carbonation depth measured. It was basically not measurable at this point, so we will get to know once the concrete is aged enough, basically 6 months or after 1 year. And for SEM3B, here we can see that the carbonated, which was not plastic protected, so here I managed to measure the CO2 carbonation depth, and here you can see like a clear border around the sample, and it showed like an average CO2 carbonation depth of 2 millimeters. So just summarizing all the work that we did. So slag initially delays strength development on concrete, but it also managed to have higher strength than even than SEM1 after 91 days. Slag clearly reduced the freezing and thawing resistance, but we also have a known limit of 50% considered. It's already known, and the testing basically confirmed it. Freeze and thaw resistance in case of without salt, especially for exposure class XF1 and XF3, it was basically dependent but quite less. It had like really low effect on the freezing and thawing due to increase of slag content. Internal damage, or that we measured via UPV, appeared to have like good or an important parameter than scaling, and it's in the case of freezing and thawing resistance without salt water. Lastly, carbonation or aging amplified the scaling significantly when the higher slag content was quite high. So that was basically, I would say, an overview of all the work in a really short time. But if you are interested in the topic, we have more information. We have published our work in Betoni magazine. So I've also provided the link, and you can also see the cover. Thank you so much. Thank you so much for your attention. Thank you.
Thank you.